Okay, so for our second lesson for this evening, this is really really focused on Math 053, section 4.5. This particular material doesn't come up in any other course. Most of the material you see appears in multiple courses, so we're often able to double up, but this is, I think, the very first one we've done which doesn't appear in anything else. But of course, as always, if you want to watch this as a preview of where you're eventually going to be, you are more than welcome to do so. Okay, for the Math 053 students, we've been going through some lessons on graphing, and I suggested that before we start this lesson that we would that I'd send you some practice questions, both to sort of recap what we've already done in the chapter, as well as because these will lead us nicely into our topic for today's class. So very quickly, we've so far looked at arguably 2 or 4 methods to graph lines, depending on 2, 3, or 4, depending on how you would think about them. So there I've listed them there as the 4 options. So the first thing we did is we just said you need to find any 2 xy pairs that make the equation true. Once you do that, then you have 2 points on the line and you can draw the graph. How do you find points that make the equation true? You either plug in an x and find the y that goes with it, or you plug in a y and find the x that goes with it. Everybody in the class could get different xy pairs from each other, but they're all on the same line, so everyone will get the same line, even though they might have chosen different pairs. And what sometimes really doesn't quite click for people at first there is that you can pick any number you want, but the key is that you are then finding the pair that goes with it for that equation, and there's only one of them. So sometimes you have to do a little bit of fiddling around, trial and error, because you want to avoid fractions and decimals. So sometimes you have to be a little fiddly with that and try a bunch of options till you find one. The second option we did is graphing by intercepts, which is really the same as the first option, except that the numbers you choose are going to be x equals 0 and y equals 0. Now, if one or both of those turns into a fraction answer for the corresponding y and x, then that's no good. Graphing by intercepts won't work. You'll have to go find other points. But when the x equals 0 and y equals 0 both give you 2 different points that don't have any fractions, that is probably the easiest way in many cases to get your graph. Then we looked at a couple special cases. We looked at equations that only have a y and not an x, and we discovered that those will be a horizontal line, like this one here, y equals -4. And we looked at ones that only have an x, no y, and that those ones would be a vertical line, like this one here, x equals 2. All right, so those are the 4 options we've got. Then I suggested that you try these, and some of you in class might have already done that, or at home, if you are watching this video for the first time, I'd suggest you pause the video and give those a shot to see if you remember how to do what we've done so far. Okay, so let's look at them. Y equals 2x plus 3. So this one we are going to do with the first method, where we're just going to find 2 points. This isn't set up great for using intercepts, because if you were to plug in x equals 0, that's really easy. But if you plug in y equals 0, you have to solve the equation for x, which is a bit of a pain. So of the options we've learned so far, just grabbing a couple values for x and plugging them in is probably the easiest. So we plug in x equals 0, and I get out y equals 3. Then we plug in x equals 1, and 2 times 1 is 2, plus 3 is 5. So 5 is the number that goes with y equals 5, goes with x equals 1. And again, we could have tried, you could have picked x equals 2, or x equals 7, or x equals -5, or y equals 6, or y equals 0. You could have picked all kinds of different things, found the partner, and everyone would have gotten 2 points that are on that line right there. There's my 2, one in red and one in blue, which I found. I think I show some others. No, I don't. Okay, I thought I plopped some other points on the graph. You can see others, though, that you might have found. You might have found x equals -2, y equals -1, or x equals -3, y equals -3, as a couple of, or x equals -1, y equals +1 right there. So lots of different points that you could have found. Pick the easiest numbers you can, and make sure you avoid fractions. This one, ding, 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 ding. As soon as you see that, you say, wait, there's an equation that has only an x and not a y. Forget everything that you've done. Don't try to find pairs of points. Don't try to graph by intercepts. Don't try to do the method that we're going to learn today. That is a vertical line. All you need to do is go over to the right 4 and draw a vertical line. So if it is missing a y, it is a vertical line. Now, sometimes people get confused with the verticals and the horizontals, so there is a really easy double check. Label some of the points on your line, like so, and make sure that in every single one of those points, x equals 4, which it does. Y changes, right? Y is all over. Y can be anything, up forever, down forever, but on this line, x is always 4, which is what we want. If you had drawn a horizontal line, you would find that there's a whole bunch of different x values, and y is always 4. That's not what we would have wanted. Okay, so it's missing a y. It only has an x. Drop everything. It's just a vertical line. Don't try and do any of the other complicated things with slope and all the different stuff that we have covered in the chapter. Okay, here's another one. We're again going to pick some points, but if we tried 0 and 1, you would find 0 works great, but if you try here, let's do it. When we plug in x equals 0, -1, you might try x equals 1 because that seems nice and easy. But in this case, if you tried x equals 1, you would find what's 2/3 times 1? It's 2/3. You have a fraction still in the equation. That is going to be not possible to graph cleanly unless technically you've drawn your grid so it's up in thirds, then I guess you could, but that's not very likely. So we picked, instead of picking x equals 1 or x equals 2, we picked x equals 3. Why did we do that? There's the work. We plug in x equals 3, which of course we need to turn into 3 over 1 because there's fraction work. And now you see exactly why we picked x equals 3, because the 3's cancel. Or if you want, you can go 2 times 3 is 6, divided by 3 is 2. Either way, you get a 2 there. So pick a value that avoids a fraction. So there's our 2 points. Plop them on the graph, and bingo, we have our answer. And again, you see some other options you might have found. X equals -3 would have also canceled out the fraction. You would have got y equals -3. That would have also drawn the same line. Unfortunately, I didn't show this over here, but if we went over just a bit more, you'd see that 6 and +3 is on the line because 6 is divisible by 3, so plugging in x equals 6 would also cancel out the fraction. Anything that divides by 3 in this case would cancel out the fraction. All right, ding, 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 ding. This equation does not have an x, it only has a y. What does that mean? It means we don't try to find pairs of points. We don't try and calculate the slope. We don't try and plot the 2 intercepts because it doesn't have 2 intercepts. This is just going to be a horizontal line right there at y equals -3. So look at the easiest way to graph. Start at the middle. Y equals negative, so down 3. There. And then everywhere to the left and everywhere to the right is where y is always equal to -3. Again, if you want to double check, label a couple points and make sure that every point on that line has y equals -3. X changes, y does not change. Okay, vertical lines, horizontal lines. And then our last one is, this guy is set up perfectly for graphing by intercepts. Why? Because, and we'll talk about this later today actually, figuring out how to choose the best method for each question. But what you see here is that the x and the y are all on one side together. And this number 12 divides evenly by 6 and divides evenly by 3, which means when I plug in zeros and wipe out one of those terms, I'm going to get a nice clean division and not end up with fractions. That's what you're looking for to graph by intercepts. So we're going to pick x equals 0 and y equals 0 as our 2 points to try. 3 times 0 just disappears, right? I wouldn't even bother writing a step that says 3 times 0 is 0. We know 3 times 0 just disappears, goes away. So 6y is 12. Divide both sides by 6. Y equals 2. And there's you see what I was talking about, that 12 divides nicely by 6, so we get a nice point there. plug in y equals 0, 6 times 0 disappears, and 12 also divides nicely by 3, so we also get a nice point for the x. So when y is 0, x is 4. There's our 2 points. Let's just remind ourselves that every point on the line makes the equation true and vice versa, so these two pairs should both make the equation true. So when x is 0 and y is 2, we get 3 times 0 is 0, plus 6 times 2 is 12, 12 equals 12, yes. When x equals 4 and y equals 0, 3 times 4 is 12, plus 6 times 0 is 0, 12 equals 12, yes. So there's the 2 points that we found by graphing by intercepts. Notice why we call it, again, graphing by intercepts, because we get the x-intercept as one of our points and the y-intercept as the other point. And again, we can see other points. Look back here. It looks like the point -4, +4 is on the graph. When x equals -4, y equals +4. You can check that in the equation if you want. 3 times -4 is -12. Hold that in your head for a second. 6 times +4 is 24. So we have -12 plus 24. Yeah, that's equal to 12. Every point that is on the line makes the equation true. Every point that makes the equation true is on the line. Okay, so we just went through those 5 graphs and practiced them. And what I want to now do is I'm going to use some of those to move on to our next idea, which is the slope-intercept form of graphing. And so we're going to take a look at a couple of the ones we just graphed, and we're going to spot some patterns in them. So there's one of the ones we just graphed, y equals 2/3 x minus 1. And what I want to notice is, I'm going to ask a couple questions here. What is the y-intercept of that graph? Well, remember the y-intercept is where it meets the y-axis. Right there, down 1. That is the point that is the y-intercept. So the y-intercept of that graph is -1. Down 1 is where it meets the y-axis. Next question, what is the slope? Well, we know we can do the slope by taking a rise and a run on the graph. So I'm going to identify any 2 definite points on the graph. I've already got one, but oh, you know what? I decided not even to use the one I had. Just to show you, I identify any 2 definite points on the graph where I can see it crosses exactly through whole number x's and y's. And then I rise and run from one to the other. Oh, I do it twice. Okay. I could have also done the whole thing, and then the fraction would have reduced to the same answer. So you see I went up 2 over 3 from this point to this point, up 2 over 3. And that would happen over and over again. Up 2 over 3, or down 2 over 3 the other direction, right? The slope will always take you from one point on a line to another point on the line. And so the slope of this line is 2 over 3. Okay, big deal. We've already done all this. Why are we doing it again? Well, take a look at this equation, which is in a very special form. Specifically, the y has been isolated, right? Y is all alone on one side of the equation. And this is interesting because the y-intercept we got was -1, which appears right there in the equation. And the slope we got was 2/3, which also appears right there in the equation. Now, is that just a fluke of this question, or is there some kind of pattern here? Guess what? There's a pattern. Let's take a look at another one. Here's another one of the ones we just did. Y equals 2x plus 3. What I'm going to remind us of first is that 2 we could also think of as 2 over 1 if we wanted to think of it as a fraction. Let's look at our graph, and I'm going to ask the same 2 questions. What is the y-intercept? Well, that's where it meets the y-axis, so up 3 right there, 0, 3. So the y-intercept is +3, up 3. What is the slope? Again, let's do some rising and running. There, I've identified a whole bunch of points. We could use any 2 of those points and rise and run. So up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. Okay, so the slope is up 2 and over 1. Little pause just to remind you that if I say I use this one and that one, then I go up 1, 2, 3, 4, 5, 6, 7, 8, and over 1, 2, 3, 4, I get a slope of 8 over 4, which is 2 over 1, right? It reduces to the same fraction. So once again, look at that. Plus 3, the y-intercept appears right in the equation, and 2 over 1, the number in front of x. So what we're discovering here is a pattern that if you have the y isolated, then the constant, the number by itself at the end, is the y-intercept, and the number in front of the x, the fraction in front of the x, is the slope. Let's try this other one. Now, we notice that this is not in that special form. It does not have y equals, but we can always put it in that form. So let's see. I want to get the y by itself, so I'm going to take this plus 3x on the left. I'm too lazy to write it, but I know there's a plus sign there, and I'm going to subtract that to the right, like so. And I did put it first because in this form, look at my equation up here, right? We have the y equals, and we have the x piece first, right? So I'm going to keep it that way. And now I want to get the y by itself, so I need to divide by 6. If I divide the left by 6, I also have to divide the right by 6. I could divide the whole right side by 6, but we're going to find it's far more convenient to separate that out and divide each piece by 6, which is the same thing. The 6's cancel on the left, so I just get a y, which is what I was aiming for. Let's look at these fractions. Negative 3 over 6, that reduces to negative 1 over 2, dividing top and bottom by 3. And 12 over 6, so that's a whole number. 12 over 6 is 2. 12 divided by 6. Okay, so now I've got this into our special form where y is by itself on one side of the equation and everything else is on the right. Let's look at the graph that we came up with earlier on when we did this by finding points. And what is the y-intercept? Where does the graph meet the y-axis? Right there. 0, 2. So the y-intercept is plus 2. Well, look at that. The pattern is continuing. What is the slope? Find any 2 points, and it looks like we're going down 1 and over 2, right, to get from one point on the graph back to another point. So negative 1 over 2. Sure enough, the number in front of the x is negative 1 over 2. The key we want to notice right now is that if an equation has y isolated, remember it has to be in this form, y equals form. If it's not in y equals form, you can't tell anything about the slope of the y-intercept. If it is in y equals form, you can just look at it and read off the slope and the y-intercept. The slope is the coefficient of the x. The y-intercept is the constant that's by itself. You remember we use the letter m for the slope. What is new here is that we also choose to use b for the y-intercept. There is no great reason for why those letters were chosen. They just seem to have happened sort of naturally through history. There's not some Latin word that is the reason for m as the slope or b as the y-intercept. It just is choices that were made. So there's 3 equations. There's the 3 that we just did. So we could have, without ever drawing the graph, we could have simply looked at that equation and said the y-intercept is 3, positive 3, and the slope is 2 over 1, right? Because 2 is a whole number, but we can write it as the fraction, 2 over 1. So y-intercept positive 3 and rise 2, run 1 for the slope. Look at this equation right over here. Without ever drawing its graph, the y-intercept is negative 1. That number subtracted at the back. The slope is the number in front of the x, 2/3. And this one over here, is the y-intercept 12 and the slope 3? No, because it's not in our special y equals form. So we don't know what the slope and the y-intercept are, but we can put it into our special form, which we already did a few slides ago. We isolated the y, you remember. And now we can just look at that equation and read off the slope is the y-intercept is +2, and the slope is -0.5, just by looking at the equation. All right, so if a question asks you for the slope and the y-intercept given an equation, and they haven't drawn you the graph, they do not want you to draw the graph. They want you to put it into y equals form and just read them off the equation, which is way easier. Okay, so what this does is this gives us a new way to find our 2 points in order to graph, using this pattern we've discovered that if we have the equation in y equals form, we can actually read the slope and the y-intercept right off of it. The y-intercept is actually a point on the graph, isn't it? The y-intercept is where it crosses the y-axis, so that's 1 point already. And then with the slope, we can rise and run from 1 point on the graph to another. So let's try a couple. Y equals -3/4 x plus 4. So that one is already, well, that's getting ahead of myself. Step 1, put it into y equals form. Get the y isolated by itself. Well, look at this. It already is. Y equals by itself on one side of the equation. Okay, so this is already in y equals mx plus b form. Step 2, simply read the slope and the y-intercept right off the equation because it's in y equals form. So the slope is -3/4. That negative should be colored blue, but that's okay. Remember, -3/4 is the same as -3/4, which is how we want to think about it. So we have a negative rise and we keep that run positive. And then the y-intercept is the number by itself, that +4. Like so. So step 3, we are going to plot the y-intercept. So if the y-intercept is +4, that simply means that we go straight up 4, right up the y-axis to 4, and that is 1 point that is on the graph, the point when x is 0 and y is 4, the y-intercept. Then from that point, we are going to use the slope to rise and run to a second point. Now, I want to point out really common error here. People will sometimes start from the origin and go down 3/4 like that. That is not what slope means. Slope does not mean start from the origin. Slope means start from any point on the graph and rise and run to another point on the graph. So here we have a point we know is on the graph, the y-intercept, down 3/4, and we get down 3/4, we get to another point that is on the graph, like so. Okay, and I've labeled it there. Labeling is a good idea. You don't have to, but generally it's nice to have labeled your 2 points if you're doing this by hand. And now we simply draw the line between those 2 points, like so. And there we have our graph. Again, a different way to find our 2 points, which is very convenient if we are in y equals form or close to it. There's the steps if you want to screenshot that for your records, or just pause and copy it down. Let's try another one. I'm going to get you to do this one, but let's get it started together to make sure you're off on the right track. So first of all is put it in y equals mx plus b form. Is the y isolated? No. Y plus 2. So the y is not by itself. I have to take that +2 on the left and move it over to the right as a -2. Now the y is isolated. Also, I'm going to remind myself that the slope here is the number in front of x, 3, but of course we want the slope to be a rise and a run, so we want to think about that 3 as a 3/1. Why don't you pause the video if you're watching and give this a try. And for those of you in class, we'll give you a couple minutes. Okay, so let's give this a try. We've got this in y equals form. We're going to identify the slope and the y-intercept by simply looking at the equation. So the y-intercept is, as we now know, that number by itself at the end, -2. The slope is rise 3, run 1, the number in front of the x. And Let's take a look now. We're going to plot step 3, plot the y-intercept straight up or down, so straight down 2. There's the y-intercept. And from that point, not from the origin, but from this point, which we know is on the line, rise 3 and run 1 to another point. Okay, now we can simply draw the line that goes through those points, just like that. Okay, so we're going to spend a few minutes here talking about how to choose which method to use. So this is all, not too bad when you graph 10 vertical lines in a row. And you're like, okay, yeah, I know how to do that. You graph 5 horizontal lines in a row. You graph a whole bunch by intercepts, right? Where this gets a little bit more dicey is when you don't know which method you should use. They just give you an equation and they say graph this line. And you're like, well, what do I want to do? So we want to talk about what you want to look for to help you decide which method is going to be the best. So there's our 5 methods that we have. We have what I said is probably the easiest when it's available, graph by intercepts. So when that is a good option, it is the fastest for sure. We have the special vertical line and horizontal line when one of the variables is missing. We have our new slope intercept method that we just learned. And then we have the original method where we're just fishing around randomly trying to find a couple points. That's actually the worst method of all, but it was a good one to start with because it taught us that any XY pair that makes the equation true is on the line, right? So, and it's kind of a last resort, but you're still going to have to go back to it occasionally. So let's look at how you would look at the equation, how you would decide which one to do. So graphing by intercepts, this is the easiest when x and y are both on the same side. So take a look at our examples down here. See, the x and the y are both on the same side of the equation in both of these examples. And you can see that you're not going to get fractions when you plug in x equals 0 or y equals 0. How can you see that? Well, if I plug in x equals 0, this disappears, and I just have negative 6y equals 30. 30 divides nicely by 6, right? When I plug in y equals 0, this disappears. I have 10x equals 30. 30 divides nicely by 10. In other words, you can see this number over on the right divides nicely by both of the coefficients. Look at this, 16. And yeah, it's negative, I know, but we don't need to think about that for a second here. 16 divides nicely by 8 and nicely by 4. And yes, they'll both be negative numbers, and that's fine. But so that's what you're looking for. Non-examples. Look at this one. 24 divides nicely by 6, right? But 24 divided by 7 isn't going to be it is going to be a fraction, which is not good for trying to create a nice graph. So you want the coefficients of x and y to divide nicely into this number over here in order for graphing by intercepts to be a good option. So that is not a good option for graphing by intercepts. And for this other one here, remember we want x and y to both be on the same side. Well, they're not. We got the y over on the left, the x over on the right. We got a fraction there in front of the x. We got all kinds of stuff going on. So this would not be a good option for graphing by intercepts. Let me go further and tell you why. Plugging in x equals 0 is fine, because this disappears and you just get y equals negative 5. Plugging in y equals 0, you have to solve that equation for x, and it's got that fraction in front of it. You just want to stay right away from that. So graph by intercepts when x and y are both on the same side. Let's go back to the examples, and you can see that the numbers will divide nicely to not give you fractions. All right, next. When do we draw a vertical line? Well, this is the one you want to hammer into your brain for the horizontal and vertical lines. When the y is missing, so there's only an x but not a y, it will be an up and down vertical line, and you simply go to that value of x. So to the right 3 for this one, vertical line. To the left 5 for this one, vertical line. Look at this one. Oh, wait a minute. Careful on that one, because x minus 1 equals 0, so you'd have to add that one to the right. Now you can see to the right 1, vertical line, right? So that is the only way to graph those equations. And I'm going to say again that people will see these after doing a whole bunch of the hard ones with the x's and y's, and they'll try to apply the other methods to these and they'll get stuck. I'm going to say 90% of my graphing questions from students, they come up and they're like, I have no idea what to do on this. And I look and it's a horizontal or vertical line. And they've been practicing the harder questions and they forgot what to do when the y is missing or the x is missing, the easy questions, right? These are the easy ones. You don't need to calculate a slope. You don't need to find 2 points that make any equations true. You just need to draw a vertical line because the y is missing. It's a vertical line. Same thing when the x is missing. The only way to do it is to recognize that it's a horizontal line. So y equals 4, go up 4, draw a horizontal line. Go down 1, y equals -1, draw a horizontal line. Third one, careful, y plus 5 equals 0, you have to move that 5 over. So we go down 5, draw a horizontal line. Okay, so vertical lines, horizontal lines, I spend so much time on them. It's a funny thing, right? Because they're the easiest ones to do, but they're the ones everyone keeps forgetting about all through the chapter as they learn other methods. Okay, so our next one here is the slope-intercept method, and that's the one that we just learned here today. When is that one going to be easiest? Well, there's a few things you want to look for. One is you want to see if the y is already isolated. You already have y equals. Um, or it's really easy to isolate the y and get it into that form. Otherwise, you're going to spend all your time putting it into y equals form when it might have been easier to do by a different method. You also want to make sure the y-intercept is a whole number, not a fraction. Otherwise, it's going to be tough to graph that y-intercept. And the last one's kind of a weird one. You want to make sure the slope isn't like a weird fraction to try to graph. So, like up 3 and over 5, that's fine, or down, even like down 5 and over 7 or something, that's fine. But when you get ones that are like, up 169 and over 450 or over 1,000 or something like that, those slopes are often those are going to arise from word problems, and graphing by slope y-intercept is not a great way to go on those because your graph isn't going to be, the scale of your graph isn't going to be built nicely for trying to apply that slope. So if we look at these ones here, we have there we go. We can see that we can read the slope and the y-intercept off of these. These are good examples here for graphing by this method. The y-intercept's a nice whole number, -5. The slope, nice and easy, up 3 over 1. Yeah, that's going to be a great one to graph easily by our new method. This one here, again, y-intercept is a nice whole number, +1. The slope is rise -2, run 3, so down 2 over 3, that's easy. The last one, careful, notice the y is not isolated, but it's not hard to isolate. Just subtract that 3 over to the right. That was easy. Y-intercept is -3, slope is 1/4. That should be no problem at all. A nice, easy one to graph by this method. How about some counter examples that would not work well for the new slope y-intercept method? Things like this. So look at this first one here. That slope, 0.127, remember we can write that as a fraction. That's 127 over 1,000. Up 127 over 1,000. If your graph is going up that far to begin with, into the 100 over 100, then probably your y scale is not going up by 1, 2, 3, 4, 5. It's probably going up by 10s or 20s or 50s or maybe even hundreds. Going up 127 is going to be pretty tricky. Maybe the over 1,000 would be fine, given whatever the scale of the graph is, but that is probably not going to be a good one to graph by slope y-intercept. Looking at this other one over here, there's a couple things going on. First of all, y is not isolated. Wouldn't be too hard to isolate it, but it would be like 3 steps to get the y by itself. If you did get the y by itself, that's what it's going to look like. And now we see all kinds of stuff going on. We see that the y-intercept, well, maybe not all kinds of stuff. The y-intercept is not a whole number. So that actually makes it even worse. This is not a good candidate to graph by the slope and the intercept method. Last one, pick values to plug in and calculate non-fraction points. So this is actually the very first method we did, but we'll use it only if the equation is not a good candidate for any of the other options. And there's going to be 2 scenarios where this might happen. You're going to see a y-intercept that is a fraction, like the one we just looked at, or you'll see a slope that is really big or really small. And again, that often comes from a word problem type scenario. In those cases, you're probably best off just picking some x values, and that makes sense in the context, that will avoid fractions, that will get rid of decimals, that will get you some good points. So I think we're going to look at a couple. So here's the 2 that we just, or well, this one's the same as the one we just did. This one's a bit different. So here we have a couple that would be good to do by just picking x or y values and calculating their partner. Not good candidates for any of the other methods for all the reasons we just discussed. So let's look at them. Oh yeah, we list. So this one, why is this not good? The intercepts are fractions, so you don't want to graph by intercepts. It's not equals y in y equals mx plus b form. The y is not isolated. If we did isolate the y, it's even worse because we find out the y-intercept is a fraction. So if instead, though, we just try some simple points, you might try with x equals 0 and y equals 0 first, but you'll find they don't give you nice answers. But if you try x equals 1, you'll find you get out y equals 1, a nice point. And if you try y equals negative 1, you'll discover you get out x equals negative 4. Oh, I thought I drew it. I guess not. So I didn't draw the graph here for you, but you could easily do that, right? You would simply take those 2 points, put them on a graph, and there you go. So when do you use the table of values method, where you pick your own values and find their partner? When none of the other methods are a good candidate. Because, I knew what the numbers to use were right away, but you probably would have had to fish around for a while trying different options, getting fractions until you eventually landed on those. So it's not the ideal way to do it, but if none of the other methods work, it will work. Over here, we can see the slope. The number in front of the variable is 0.22. And we have a word problem here. Cost of renting a car for a month to drive across Canada, I have no idea if these numbers are right, is $700 plus 22 cents per kilometer. So the slope is 0.22, which is 22 over 100. Or if we want, could reduce to 11 over 50. That is going to be difficult. Let's think about our scale here. We're driving thousands of kilometers, and we want to try and do a rise of 11 and a run of 50. Our graph probably won't even show the 50s, right? Because if Canada is over 5,000 kilometers wide, you're not going to be able to run 50 accurately. You're definitely not going to be able to rise 11 accurately, because you're probably not, your y-axis won't have those small divisions, right? So this is not a good candidate to use any of the other methods on. Yeah. However, if you pick a couple values that make sense in the context of the question, and again, you might have to try a few until you get ones that are good, but knowing that Canada is well over 5,000 kilometers wide, somewhere between 5 and 6, there's a couple good options. When d equals 0, if you plug that in, you'll find that the cost when you drive 0 kilometers, so if you just rent your car and don't go anywhere, you pay $700, obviously, because that's what you paid them right off the bat. If you drive 5,000 kilometers, then it's going to cost you $1,800. Those points are okay. There's a couple points you could graph, right? So when none of the other methods are good candidates, go back to pick a couple values, plug them in, find their partner until you find some decent points to plot. Okay, we still have ways to go. I forgot. This is a really big lesson. Parallel and perpendicular lines. So we say that two lines are parallel if they never meet, even if you imagine extending them out infinitely in both directions. So there, that red and green line, those are parallel lines like railway tracks, right? They will never meet. So hopefully you can see that obviously, since the very thing slope measures is how steep a line is, clearly parallel lines must have the same slope, which we can see by checking this. Let's grab a couple points there on the green line. We can see its slope is up 2 over 3. Let's grab a couple points on the red line. Again, I just picked any two sure points. There would have been more options in there. And the red line is also slope of up 2 over 3. Think about it, makes sense, right? If both lines are always rising and running up 2 over 3, up 2 over 3, they will never meet each other. They are parallel lines. So that means we can test if lines are parallel by simply finding and comparing their slopes. How do we find their slopes? Not by taking a whole bunch of time to draw their graph, but by simply putting them into y equals form, because we know the slope is the number in front of x. So here's some 3 lines, and the question is, are any of these parallel? Well, let's find their slopes. Let's look at the first one. It's already in y equals form. Look at that. So that means I don't need to do anything. I can just look at that equation and I know the slope of that line is -3/5. What about the second one? Is it in y equals form? No, it's not. So we're going to have to put it into it. We know this is a plus 5x and this is a plus 2, even though we're too lazy to write it. So I'm going to take the plus 5x and I'm going to subtract it over to the right because I want to get my y by itself. Now I divide both sides by -3, and remember we discovered the easiest way to do that was divide both of the separate pieces on the right by -3. Those ones cancel, so we get y by itself, which is the whole point. -5 over -3, negative over negative actually turns out to be positive, 5/3. We could actually stop right there, but let's write our final thing. 2 over -3 is a fraction, negative, because it's a positive divided by a negative, -2/3. Okay, there's the slope of our second line, 5 over 3. Are these two lines parallel? No, they are not, because they do not have the same slope. So we don't even need to draw them. We just find the slope, and we know they're not parallel. Let's look at the third one. Once again, we need to get the y by itself, so we have y equals mx plus b form. I subtract the 9x to the right. I divide everything by 15. 15's cancel on the left. -9 over 15, let's reduce that fraction. Top and bottom both divide by 3. So it's going to become -3 on the top and +5 on the bottom, or I move the negative out front, as you recall we can do. So -3 over 5 is the same as -3 over 5. And 3 over 15 reduces to 1 over 15. Look at these equations for a sec, by the way, before we finish this up. You do not want to graph these. The first one's fine. Y-intercept is a nice whole number, then rise and run. This one has a fraction y-intercept. That would be really hard to graph. This one has 1/15th is the y-intercept. That's fine. You can go up 1/15th and plot it. It's just it's not going to be hard to plot accurately on the grid you're using. So you would want to find a different method to graph this line. Look at the slope of the third line. It's -3/5. Let's erase all that stuff in the middle, because now we can see these two lines are parallel. They both have a slope of -3/5. We didn't need to draw them. I think I do graph them for you here. We have discovered the lines defined by those two equations are parallel. That's just the two we have here, right? This one and this one. They both end up having the same slope. We didn't even need to graph them, thank goodness. Yes, they would have been monsters to graph, but we could have if we wanted, and there they are. Sure enough, the red line and the blue line. If you do graph them, you discover they are parallel. Why are they parallel? because slope of negative 3/5, I might not have two sure points I can do that with. I don't actually. Oh, I have one here on the blue line. 1, 2, 3 down, 1, 2, 3, 4, 5. So a rise and a run from this point to this point, down 3 over 5, just like we expected. Last topic, I think. Lines are said to be perpendicular if they meet at a right angle. So there's a couple lines, and hopefully the resolution, if the resolution on your machine is different, it's possible that those won't look perpendicular to you if it's stretching your graph either to the right and left or up and down, but hopefully those look perpendicular to you. They do on my screen. So they meet at a right angle, like two cross streets meeting, right? They're at a right angle. So let's look at the slopes of those two perpendicular lines and see if we can figure out how to recognize if lines are perpendicular. So the red one goes up 2 and over 1, positive 2 over 1, like so. What about the blue one? Find 2 points. There we go. There's a couple points I found. Again, you could find any 2 points as long as there's sure points on the line. That one went down 2 and over 4, and that reduces to negative a half. Or you might notice I could have just gone down 1 and over 2 and got the same answer with a little less work if I had picked those 2 points. What do we notice about these two slopes of the perpendicular lines? Well, I want you to notice that one is positive and the other is negative. Well, if you think about that, that makes a lot of sense, because how could two lines meet perpendicularly, meet at a right angle, unless one was sloping up and the other was sloping down, right? That's the only way they can meet at a right angle. The other thing you notice is that one of them was 2 over 1 and the other was 1 over 2. Now, if only one of those things had happened, but not both of them, if one was positive and one was negative, but the slopes weren't the flip of each other, they wouldn't have been perpendicular. Or if the slopes were the flip of each other, but they were both positive or both negative, then they would not be perpendicular. So both of those things need to happen. So they have the opposite sign and they are flipped upside down from each other. The fancy math phrase we use for that is that they are negative reciprocals. Negative meaning they have the opposite plus or minus sign. Reciprocal is fancy math word for flipped upside down. So let's look at a few here. There's some slopes on the left, and we're going to identify what the perpendicular slope is on the right. So if m equals negative 1 over 2, the perpendicular slope will be positive 2 over 1, which we could also just call 2. So negative a half slope is perpendicular to positive 2 slope. Positive 2/3, the perpendicular slope will be negative, so opposite sign, 3 over 2, flip the fraction. m equals 5, we better remind ourselves that 5 is actually 5 over 1, so a slope of positive 5 over 1, the perpendicular slope is negative 1 over 5. What about this one? Negative 0.7. Well, remember that that's actually 7 over 10, right? 0.7. So that's negative 7 over 10. So the perpendicular will be positive 10 over 7. Flip the sign, flip the fraction. And we don't have to write the positive, of course. We could just write 10 over 7. Okay, so let's take a look back at our earlier example where we were looking at the parallel lines. So those are the three equations we looked at, and we did the work and we calculated all of their slopes. The first one, remember, was already in y equals form, so we just looked at it. The second one, we had to isolate the y, and we eventually calculated the slope. And the third one, we also had to isolate the y, and eventually we're able to read the slope off. So what we discovered when we did this before is that the first line had a slope of negative 3/5, and the third line over here had a slope of negative 3/5, so they were parallel. all we said at that time was this line was not parallel, but now we can look at this and say, well, actually, okay, it's not parallel, but look at this, negative 3 over 5, positive 5 over 3. So this middle line is actually perpendicular to both of the others. It meets both of those lines at a right angle. Yeah, perpendicular to both the other two, and I think I'm going to put those on a graph for you. These would be nasty to graph. The first one's fine, y-intercept of 2 down 3 over 5, no problem. This, though, y-intercept of 5/3, that's 1 2/3, yuck, that's going to be hard. This one's even worse, a y-intercept of 1/15. I mean, it's there, it will be on the graph, but it's not easy to graph. So you do not want to graph the second or third line here by the slope-intercept method, but there would be other ways of graphing them, by maybe just by finding 2 points, right? Our first method that we can always fall back on. So there we've got the 3 equations in 3 different colors. We've reminded ourselves of what those slopes are. The middle one is perpendicular to the other 2 because it has the opposite sign and the fraction is flipped. Sure enough, when you look at these, the red and the orange one are parallel to each other, as we already saw, and the blue one crosses them at a 90-degree angle. And that is the idea of parallel and perpendicular lines.